what name even maybe the name Thy kingdom come, that will be done on us as it is in heaven. Give us our daily bread. Give us.
As we forgive those who trespass against us, lead us not into temptation, but deliver us from evil. Amen.
Amen. Thank you so much for that opening prayer. Okay, I want us to kick off with one more example in line with the mathematical induction of sums of series. Then we will kick off to definitely divisibility and multiple tests. One more example on sums of series. One more other example. Let's say other examples. Other examples. One that is the part B people have been talking about. Number one, part B. Number one, part D. What did it say? So part B, number one, it was in line with this kind of arrangement. One was supposed to prove by induction. One was supposed to prove by induction, proving by mathematical induction that this is true. Proved by mathematical induction that is true. So what is the series? What's the series? When you deduce the series, what do you see? At r equal to 1, you will have 2r minus 1 all squared. Feed a 1 there. You get 2 minus 1, which is 1 squared, which is a 1. Compute it. Plus, at 2, you will have 2 times.
I think we can't see your board.
Sorry for that. That was the part D. That was the part D. That was the part D. And I've been saying that we are deducing the series. When you feed in this expression, when you feed in r as 1, I was not saying that you see a 2 times 1, which is 2 minus 1, which is 1 squared. Feed in a 2, you get 4 minus 1, which is 3 squared, which is a 9. And let's get one more term. At 3, I say 6 minus 1 squared, which is 5 squared, giving me a 25. And that sequence continues up to the nth term. At r equal to n, you get 2n minus 1 squared, which gives us n into 4n squared minus 1 over 3 as the series sum at the nth term. So at that point, after generating that series, which we discussed last week, just check on the channel if you are not getting how we are generating that series. Just check on the channel, you will be enlightened further. Yes. Now set n to 1. When n is 1, we are now testing whether the series is true. When n is 1, on the left-hand side, that will be a 1. However, on the right-hand side, when n is 1, I will get 1 into 4 into 1 squared minus 1 out of 3, which is 4 minus 1, which is a 3 in brackets there, 3 over 3, which still gives us a 1. So at that instant, it's true that at n equal to 1, the series is correct. What about when n is equal to 2? When n is equal to 2, that communicates that take the first two terms of the series on the left-hand side. So on the left-hand side, I will take the sum up to the second term, that's 1 plus 9, which is 10. However, on the right-hand side, I will have n as 2, that will be 2 into, in brackets here, I will have 4 into 2 squared minus 1 out of 3. What does that communicate? What does that communicate? That gives me a 2 times 4 times 4, that is yet 16 minus 1, you get 15 over a 3. So I see up there a 30 over 3, which gives me a 10 as well. So we normally put a statement aside, proof holds, but it's still clear that the two sides balance. Even if someone doesn't mention it, you will still be safe. Now, having used the any two terms and we are safe that the series is true, we can now go to the assumption stage. At the assumption stage, that's when we say, when n is equal to a constant we don't know, assume assumption stage. Assume true false. Assume true false. So if it does hold, what will happen to the series? That series, wherever we have n, that series will be taken up by k. So we'll have 1 plus 9 plus 25 plus up to the nth term, which was 2n minus 1 all squared. But where there is n now, I'm feeding k there, all squared is equal to n into 4n squared minus 1 out of 3, in that order as my assumption stage. Then we go to the induction stage. When n is equal to k plus 1, we have now to confirm the induction for any value of n. When n is k plus 1, what will happen? The series will progress up to the nth term at k plus 1. Up to the nth term at k plus 1. Remember, where we had n, k was taking up that position. K was taking up that position. So even the sum had to take up k. Sorry for that. I think someone. Okay, thank you. So that sequence again must progress up to k plus 1, but the term in k can be mentioned. But at k plus 1, what will the nth term be?
It's 2k. It's 2k plus 1.
Someone says it's 2k plus 1. How is he getting that? That person is substituting n here as k plus 1. Someone who is not getting it, feeding k plus 1 there. 2 into k plus 1 minus 1, but the whole quantity all squared. You'll say 2k plus 2 minus 1 all squared, which is 2k plus 1. And that way, which is 2k plus 1. So down here, our nth term at k plus 1 is 2k plus 1. Then similarly, at the side of the sum, feed in k plus 1. So you will have k plus 1 take up n into the 4 into k plus 1 all squared minus 1, but the whole quantity divided by 3. That way. So now from here, again, we have to choose the left-hand side. What is the left-hand side communicating? It's the 1 plus 9 plus 225 plus 2k minus 1 all squared plus 2k plus 1 all squared as well. That's the left-hand side. And the right-hand side, is k plus 1 into 4 into k plus 1 all squared minus 1 all over 3. So we must ensure the left-hand side balances with the right-hand side. However, the summation is a recap for anyone who is not yet there, because this is what we did in the previous episode or lesson. The sum from the first term up to 2k minus 1 all squared, we know it. We know that sum. It's this sum here. It's this sum here. It's this one here. That's the sum. From 1 up to 2k minus 1 all squared, you get that k into 4k squared minus 1. So we are going to just substitute it here as k. That statement there, that statement is k into 4k squared minus 1 all over 3. We are adding on this quantity here, which is 2k plus 1 all squared. So simplify these two to arrive at this quantity on the right-hand side. We must achieve the quantity on the right-hand side using those two on the left. So where we are now, obviously someone should be able to notice that we have an LCM of 3 to appreciate. When you appreciate that 3 as the LCM, you will now obtain k into 4k squared minus 1 plus this over 1, 3 by 1, you will get 3 into 2k plus 1 all squared, like that, in that way. And then that pushes us to say this is the same as when you try to simplify, there is no common factor there. So you have no choice except looking at it as 4k, not really. Someone should see this k into 2k all squared minus 1 squared plus 3 into 2k plus 1, which pushes us to say, pushes us to a statement like, the statement like this is a 3, and then you write k. I don't know whether people have seen a difference of 2 squares there, which is 2k plus 1 into 2k minus 1 plus 3 into 2k plus 1. There's a difference of 2 squares there. So depending on what we want to come up with, I'm certain that we can now take out 2k plus 1.
Sir,
Yes, please.
sir, that part has confused me. Where you split,
Where?
like, how do you come up with the difference of squares? Like that part above that one that we're seeing now.
That one?
Hmm.
Look at
Yes, like
look at this 4k squared. 4k squared can be the same as 2 squared k squared, and that product can be put in 1 as 2k or squared. But taking off a 1, that 1 is the same as 1 squared. It doesn't change. Clear?
yes.
Okay, that's how I come up with the difference of 2 squares to help me factorize. When you take out 2k plus 1, inside you will have k into 2k minus 1 plus 3 into 1 2k plus 1. And there is a 3 waiting out here. So that statement can be put down as 2k plus 1 over 3 into, when you open in brackets, you get 2k squared minus k plus 6k plus 3. And that quantity will lead us to say this is 2k plus 1 over 3 multiplied by 2k squared plus 5k plus 3 there. That one. That's how it would look like. However, the quantity we want, hope you see it. So what can we do? Is that factorizable? Is that quadratic factorizable, class?
No.
We have factors of 6 that can give us a positive 5.
No.
We have factors
2
of
and
6.
3.
Okay.
Yes, we have
2 and 3.
2 and
3.
2 and 3. Okay. So, okay, the person who was saying it's not factorizable, hope is sorted. That is 2 and 3. We can use 2 and 3. We can use 2 and 3. We can use 2 and 3 there. Let's try to factorize from the sides here. So we want to factorize 2k squared plus 5k plus 3. That is the same as 2k squared plus 2k plus 3k plus 3. And that is the same as taking out 2k here, and you get k plus 1 plus 3 into k plus 1. So the two factors are 2k plus 3 multiplied by k plus 1, that way. So the resultant here, the resultant is 2k plus 1 into, this is now yet another product, k plus 1 into 2k plus 3, all over 3. So the extension we see, the 4 into k, this extension here, we can reach it either way, by expanding or by just simplifying what we have here. The choice is ours. So for me to write it as it is there, the choice will remain mine. So the k plus 1 is before, the k plus 1 is the one out in the statement we want to get. So I can write k plus 1 out. That means these two, when you multiply, they give us what we have there in the bracket over 3 weighting. So if we want, we can confirm, because this is the same as also our right hand side is the same as k plus 1 into, I can create yet another difference of 2 squares, 2 into k plus 1, but the whole of it squared minus 1 squared. But remember, there is a 3 weighting. I want to show you that they are the same. K plus 1 over 3. Inside here, you will have 2 brackets. 2 into k plus 1 plus 1. That's the first bracket. Followed by 2 into k plus 1 minus 1. And that pushes us right. K plus 1 over 3 into 2k plus 2 plus that one which is a plus 3 into, open brackets there, 2k plus 2 minus 1 which is a plus 1. So 2k plus 3 and 2k plus 1 times that k plus 1 is similar to what we have this side on the right, on the left hand side rather, which confirms that that sequence, that series holds for any integral value of n. So at n equal to k plus 1, still proof holds. Not to make it so long, I just pushed the right hand side as well closer to my left hand side where we have factors. That was the trick in that. So draw the conclusion. Since proof holds, for n equal to 1, 2, k and k plus 1 and k plus 1. Thus it's true that the summation from r equal to 1 to n of 2r minus 1 all squared is equal to n into 4n squared minus 1 over 3 for all integral values, of n, for all integral values of n. That was the recap for the proof by induction in line with the sums of series. That was the recap that we had to do. That was the recap. However, today our main subsection is divisibility. We want to handle divisibility and multiple tests. Divisibility and multiple tests. Divisibility and multiple tests. Proving by induction that a certain expression is divisible. Proving by induction that a certain expression is a multiple of another, is divisible, is a multiple, is a factor. Divisibility and multiple. Under divisible, you can use a statement like factor. all of those, but keeping in mind our concepts of proof by induction. The general concepts still hold. Examples, the general concepts we know still hold. Okay, so for example, our first example here is, number one. Number one is here, prove by induction. Prove by induction that is 3 to power 2n minus 1, 2n, 3 to power 2n minus 1. That negative 1 is not in the power of 3. It's another term. Minus 1 is divisible by 8 for all natural numbers n. Divisibility and multiple tests. So how do we start? We start by abbreviating or setting that quantity we have been given to an expression of our choice, and also appreciate the statement divisible. So we are going to let the result of the divisibility for any value of n be a letter a subscript n. As any values, you get different answers for the statement 3 to power 2n minus 1 over 8. They are different constants, they are different integers you will be getting as any values. When n is 1, you will get the first solution from that quotient. When n is 2, you get another one, and so on. So that's what we want to check, that whether it's true. We want to check whether that is true, whether it will be true for many numbers n. So as we check whether that is true, we can make it more appealing by saying, if this quantity is divisible by 8, then it can be a multiple. It can be expressed into different values as multiples of 8. After all, it's divisible by 8. If you get this expression as 8, it means it's as if it's 8 times 1. When you divide by 8, the value of a will be 1. If you get it as 16, it means maybe the quantity in it is 8 and times 2, meaning a is 2. If you get it as 32, it means it is 8 times 4, meaning the other value a is 4, and so on, and so on. I'm just introducing this. It stands for the value you get when you divide that expression 3 to power 2n minus 1. Someone is asking what n stands for. That is any constant you get having divided that quantity by 8. That constant you get, but it varies with the different values of n. That's when it has a subscript n in it. It is any value you can set. Any letter can be used as long as you attach it to a subscript n. So for that divisibility to be true, we are going to first of all check for the first two values. When n is 1, what will happen? You will be looking for the first divisible, or the first constant after dividing, which is 3 to power 2 into 1 minus 1. That is actually 3 squared, which is 9 minus 1. And you notice that I get 8. So 8 is the same as 8 times 1. By virtue of the fact that I can get 8 from this side, I can generate an 8. It is enough to confirm that proof holds. Because the moment you divide by the 8 as we had put it this side, you'll get your first solution as 1. What about at n equal to 2? Let's check it at n equal to 2. Let's check it again. When n is equal to 2, what happens? You will have 8a subscript 2 giving us a 3 to power 2 into 2 minus 1, which is 3 to power 4. What's the 3 to power 4, class? 3 to power 4 will be what here? 3 to power 4 minus 1.
80.
80. Because 3 to power 4 is 81, take off 1, you get 8. So can I write 8 as a multiple of 8 to confirm that it's divisible by 8? What should I write? It will be 8 times
8
what?
times 10.
8 times 10, which is enough to confirm that proof does hold again. Proof holds. Are we together at that level of checking whether the expression we are given is divisible by 8?
Yes.
Let's use the chart. I want to see those who are following me. Reply in the chat if you're okay at that stage where we are. Thank you, Regan, Pius K, Elvis, Benjamin, Lee, Losias, Raymond. Thank you. Thank you. Caleb is okay. 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 For the first example, I will entertain questions. Stephen, switch on your mic and let me know where you're lost from. Stephen, if that issue you have, can you raise it? Okay. I'm hearing you. Can you talk?
First repeat for me the part of AN.
The part of what?
That AN, that constant.
You've answered the question. AN is a constant. Because if this expression was 16, divide it by 2. That 2 is the AN. But you're getting it after setting. When do you get 16? You get 16 at a certain value of after setting n to a certain value. Just like we have been able to get 8 from it after setting n to 1. So the answer 1 is the constant A1. The constant at n equal to 1 is 1 after setting n to 1. It's a constant, just like you've said it. There's no magic in that. But we are just checking that that constant will be true for all values of n. It will be a constant. It will be an integer. Just because what makes it an integer? Only and only when the expression 3, only and only when this expression 3 to power 2n minus 1 is divisible by 8. That's what makes n a constant. And that's what we are proving. We are confirming that it's a constant all throughout. So progressively, we are supposed now to say that when n is equal to k, and what do we say when n is equal to k? We have confirmed 2 stages. And someone remind me, what do we say when n is equal to k?
we assume that the thing is divisible by.
Assume proof holds.
Good. That's good. All of you are right. Assume proof holds. It's the assumption stage. In other words, assume proof holds. That implies where we have n in that expression, in this expression here, wherever we have n, we should substitute there k in that expression. Where we have n, we should replace it with k. So that means we will have 8a down here. We will have 8a k as 3 to power 2k minus 1. Minus 1. So from there, we progress. From there, we will progress. From there, we will have to progress. From there, we will have to progress. As we progress, we are now going to suggest that when n is equal to k plus 1, when n is equal to k plus 1, what are we going to say? Just in a bit. When n is equal to k plus 1, what are we going to say? Remember, our last stage was at n equal to k. So we have just made an assumption at k as so. Now, what about when n is equal to k plus 1? What will happen? Our induction stage, which was just to share the whole screen, not to be disturbed a lot. Our induction stage, or our expression we are deducing, is 8an 3 power 2n is quoted here, 3 power 2n minus 1. I have to pick it and keep it in mind. When n is equal to k plus 1, what should it become? What should it become? This should become 8a k plus 1. Still, you will substitute n as k plus 1 equal to 3 power 2 into k plus 1 minus 1. Now, we have to ensure. How can we deduce that the induction has occurred? By ensuring that this side also becomes a multiple of 8. 8 times any constant that we will obtain, for that matter. Yes, Joshua. Okay. Now, just like in the sums of series, we're using the assumption stage. Even this time around, we are going to employ the assumption stage. In the assumption stage, I want us to notice that from this step here, from that assumption stage, I can write 3 power 2k as the subject. That index in k is the same as 8a subscript k plus 1. I want people to agree about that. From this statement here, make that 3 power 2k the subject. Make that 3 to power 2k the subject. What will happen when you do make it the subject? It will be 8a subscript k plus 1. Now, my intention is to substitute it in the statement at n equal to k plus 1. So 8a at k plus 1 is equal to 3 to power 2k multiplied by 3 power k minus 1. This statement here, is 3 power 2k plus 2, minus 1. If you reverse it by rows of indices, you can write it as, you can end up writing it as 3 to power 2k times 3 to power 2 minus 1. And this quantity here, 3 power 2k, we have it here. We have it here as 8a subscript k plus 1. It's being multiplied by 3 squared, which is 9, minus 1. So when that 9 enters the brackets, you will have 8 times 9. You will have 8 times 9, which is a 72. 72a subscript k plus 9 minus 1. And which that ends up as, we are interested in creating a multiple of k to confirm that proof does hold still. This is the same as 72a k plus 8 if you do agree. So at that level, I'm comfortably able to take out 8, to factorize out 8, and I will get 9, 9a subscript k plus 1, which is equal to, maybe to show someone the statement, that statement is equal to, this is what it is equal to. It's equal to that, which is equal to 8, which is equal to 8, which is equal to 8ak plus 1. That statement is 8a k plus 1. So at k plus 1, the 8 as a multiple is still possible, which confirms that still proof holds. Every time you get that 8 out, that means at that point, at k plus 1, the expression will still be divisible. The expression at k plus 1 will be still divisible. So proof holds at n equal to k plus 1 as well. Just like we have proved previously that it does hold.
Excuse me, sir.
Yes, please.
Sir, I'm kind of lost where we're substituting for k, for n is equal to k and n is equal to k plus 1. Why do we add like 8a k? Why don't we say a k plus in the 8 as a multiple of?
I beg your pardon? Why do we do what?
Yeah. Sir, why are we like multiplying by 8? For example, when we're substituting for n is equal to k and n is equal to k plus 1, why are we multiplying that 8?
It was there.
Why are we making it a multiple?
It was there. It was there. There are two options. Using this, I didn't want us to have a fraction. I didn't want us to move with the fractions. That's why I cross multiplied. But that 8 was there with respect to the statement divisible by 8. That 8 was. You see that 8 down there?
Oh,
it's
yes,
what
sir.
we shifted to become a multiple.
So you. So you were just cross multiplying, I think.
I just cross multiply. Is it okay?
Okay.
So
Yes, sir.
so in conclusion here, you again say the same statement since true false, for n equal to 1, true k and k plus 1 and k plus 1, thus it is true, thus it's true that 3 to power 2n minus 1 is always divisible, by 8 for all natural numbers n. For all natural numbers n. That conclusion statement must be seen. Are we together?
Yes, sir.
Thank you. Thank you. Okay, someone wants to look at the upper stage a bit as we get example 2 in that line. As we get example 2. As we get example 2. Okay, in example 2, in our example number 2, we are asked to prove by induction that 8 power n minus 7n plus 6 is a multiple of 7. So that implies straight away in the solution, someone would say for that quantity to be a multiple of 7, then it means that it is divisible by 7. Am I right? For a quantity to be a multiple of a certain number, then it must be divisible. It must be divisible by that number. So that implies if I say f at n is equal to 8 power n minus 7n plus 6 divided by that quantity 7. If that quantity is to be divisible by 7, then the values at any value of n you get are multiples of 7. So 7 fn on cross multiplication is 8 power n minus 7n plus 6. And then you start checking when n is equal to 1, we'll have 7f at 1. The first value you get, that is at 8 power 1 minus 7 into 1 plus 6. That is 8 minus 7 plus 6. I don't know whether people see a 7 there. A 7, which is true, that true false. The 7 we have got is obviously divisible by 7. What about when n is equal to 2? You will have 7 f of 2 equal to 8 squared minus 7 into 2 plus 6. What is that one equal to? Let's submit in the chat. If you've got it, what is that one equal to?
$56. Sir, 56.
56. So that's good. That's good. So is 56 a multiple of 7? That 56 as a multiple of 7, it's 7 times what?
times 8.
Good. 7 times 8. It's a multiple of 7. That implies that you prove false. So we on track. So you can now go to the assumption stage and say when n is equal to k, when n is equal to k, 7f at k will equal to 8 power k minus 7k plus 6. Assume proof false. Don't forget. Make the assumption statement, then go and confirm at a known stage beyond k. When n is equal to k plus 1, this will be 7 at k plus 1 equal to 8 power k plus 1 minus 7 into k plus 1 plus 6. We go back to the same expression and replace n with k plus 1. However, we have to use our assumption stage to confirm the stage where we are. Now, from that assumption stage, I want us to make the index statement the subject. 8 power k is what in terms of the other terms? When you make it the subject, what do you get?
It's 7fk plus 7k.
7fk plus 7k
Minus 6.
minus 6. Thank you. Now come to our expression in k plus 1. 7 at k plus 1 is equal to 8 power k times 8 minus 7. We can keep this one, k plus 1 plus 6. Now let's substitute in here. Let's substitute for this as this quantity. It will be 7f at k plus 7k minus 6, but there is some 8 waiting out here, minus 7k minus 7 plus 6. That gives us, when you enter brackets, you will have a 56f at k plus a 56k minus a 48 minus 7k minus 1. This gives us a minus 1. So simplify, what do you see? What do you see? That is 56f at k. 56 minus that 7, what does it yield?
49.
49, good. 49k. Then a minus, what about a minus 48 and a minus 1? What do you get?
Minus 49.
Minus 49. That is our 7f at k plus 1. Now, is it possible to factorize out a 7 to create a multiple at k plus 1? You say 7 out?
Yes.
What is this? What's that 7 giving us inside?
Yes.
Is that 8 at k plus 7k
Yes.
minus 7? Not so.
Yes.
Which is a confirmation that proof holds. Which is a confirmation that proof holds. And we can just conclude down here that since proof holds, for n equal to 1, 2, k and k plus 1, it's then true. It's then true that 8 power n minus 7n plus 6 is a multiple. of 7 for all is a multiple of 7 as stated for all integral values of n. For all integral values, of n.
Sir, I have a question.
Yes, please.
So what if you just be like, since or proof holds for n equals 1, 2, 2k and k plus 1, it's divisible by 7, and after, is it right?
You must pick up the statement in question. The words may not matter, but as long as you capture the statement in question as well.
Sir.
Yes, please.
Sir.
Yes, please.
I have a question. There's that step where you made 8k to be the subject of the equation. I need to understand why you did that.
Remember, just like in the sums of series, when proving by induction, we use the previous assumption stage. We apply the assumption stage. So the assumption stage must be employed. And in my previous example, I used the index. That was in there, which was a 3 power 2k. Look at the index in question at k and make it the subject. To easily do it, I'm giving the shortest path. Even here, the index at k is 8 to power k. I make it the subject. Okay?
Okay.
You make it the subject because as a must to prove by induction at k plus 1, you must employ some stage from the assumption stage. You must utilize an expression from the assumption stage, as we have been doing it from the beginning. Is it okay?
Sir, some other questions.
Yes, please.
So
is it possible for us to
can
use
that like that last step?
Sums of series. 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 That's our last subsection. Sums of series. And for that subsection, it's important to recall. The standard or the general sums. That's why in the introduction I say, under sums of series, to determine the sums of different series, we must recall the general summations of the following series. That is to say, 1, we proved by induction that the sum of series from 1 up to n terms of R is the same as a half into n plus 1. 4, such a series may be put down as 1 plus 2 plus 3 plus and so on up to n, which is the same as a half n into n plus 1. That's a reminder. Still, we said that the summation from R equal to 1 to n of square numbers is the same as 1 over 6n into n plus 1 into 2n plus 1, and such a series, or these are alternatives of deducing those statements, or it's where the series can be put down as 1 squared, 2 squared, 3 squared, which is true up to n squared, up to the n term, nth term, which is 1 over 6 to n into n plus 1 into 2n plus 1. Those are general summations that you must keep friendly to you for easy interpretation of what we are going to do. 3, the sum from r equal to 1 to n of cubic terms, cubic numbers, is a quarter of n squared into n plus 1 squared. Or someone can write it as 1 cubed. You meet 1 cubed plus 2 cubed plus 3 cubed plus, and so on, up to the nth term n cubed. Just know that series sums up to a quarter n squared into n plus 1 all squared. Very important summations. And how do we refer to them? To get sums of different series, let's review that under examples. 1. The first example is to find the sum. Find the sum of any terms. Find the sum of any terms. Find the sum of any terms of a certain series below. So when you look at that series, it is 1 plus 2 plus 3 plus, and so on, up to the nth term to n plus 1. Now the difference from the general one is what the learner must observe. The difference from the general one. The general one, 1 plus 2 plus 3, it goes up to any terms. It doesn't go up to 2n plus 1 terms. I want to be quoted very well. The series we have been given, it's any term, nth term is 2n plus 1. But the standard one we know. For us, we know that 1 plus 2 plus 3 plus, and so on. This is some quoting the standard one we know, from which goes up to n is equal to a half n into n plus 1. It's the standard one we know. And this here, this one here, is put down as the sum of any terms, which is given as a half n into n plus 1. But the one we want doesn't go up to any terms. For it, it goes up to 2n plus 1 terms. So what do I do? It's a matter of substitution. So this implies that the one I want, which is the sum of 2n plus 1 terms, will equal to this very one, but when n takes up a new position, 2n plus 1 into 2n plus 1, but there is a 1 waiting. So that becomes a half into 2n plus 1, open brackets here, you get 2n plus 2. That 1 plus that 1, you get a 2. And if you're careful, you realize that that half will reduce the 2 in the other bracket to give us n plus 1. So therefore, the sum up to 2n plus 1 terms of this series is equal to n plus 1 multiplied by 2n plus 1. So let's say this implies, then therefore, let's rewrite the given question. The given question was the sum up to 2n plus 1. So we can now conclude and say 1 plus 2 plus 3, the series up to 2n plus 1 is equal to n plus 1 multiplied by 2n plus 1. That is its sum. That becomes its sum. Yes, Owen. Let me entertain a question. Yes, Owen.
Sir, I'm asking. So for that,
you can use the chat. Your network is not okay.
Or you have to cram it.
I beg your pardon. Let him use the chat.
Would you have to cram the standard statements or
what? Those standard statements, you missed the first lesson. Those standard statements, as long as you know how to use them, those standard statements are in your mathematical tables for you to relate, to refer to them. They are in your mathematical tables. Any other person asking, you can use the chat for us not to be lagging. I want to do one example, part B. Part B. Part B. Part B. Part B. You should be able to notice that in part B, we have this kind of statement. We have this kind of statement, 1 squared plus that. We want to get its sum. I think we can recall that for us, we know that the sum of n terms of such square numbers is 1/6 into n plus 1 into 2n plus 1. But this question wants us to get the sum of n minus 1 terms of the square numbers. The sum of n minus 1. So what will this become? This will be 1/6 into n minus 1 into where there is n, replace n minus 1 continuously. Where there is n, replace n minus 1. Where there is n, replace n minus 1. And that will be 1/6 into n minus 1 into n into 2n minus 2 plus 1, which is a minus 1 there. And in conclusion, a candidate can leave that at that level as the sum. So that means therefore 1 squared plus 2 squared plus 3 squared up to n minus 1 all squared is the same as 1/6 n into n minus 1 into 2n minus 1 at that instant. I want us to pick up from there next time, but the moment we conclude this, we'll be shifting to trigonometry. I believe our next session will not be entirely on this. We just conclude it and push to the next bit.
Sir,